Patty's Calculus Videos, written and performed by me, Patty Leitner.
Part 3. Applications of the derivative. Section 4.7. Optimization problems.
Lesson 2. A rectangle trapped under a curve. So, the second example, it begins on page 3 of this section, is a little bit less applied looking, but there are some problems in the homework section that are similar to this and that describe a more physical kind of situation. But this is a typical optimization problem, so I wanted to put it in there. And the mathematics in it, the calculations, are slightly more difficult than the one that we just looked at. So let's see if we can read through this and do part 1 together, draw the picture, and then I'll go ahead and have you stop the video at different points and think about each of these other parts on your own. Okay, a rectangle has 2 lower corners on the x-axis. So we're going to have some kind of rectangle that sticks up above the x-axis, and 2 of the lower corners are right on the x-axis. 2 upper corners are on this curve, y equals square root of 1 minus x squared. So 2 lower corners are on the x-axis, and 2 of the upper corners of my rectangle are on that curve. But what does this curve look like? Well, let's see if we can think about it for a moment. If you think about y equals square root of 1 minus x squared, if I were to square both sides of this equation, I would get y squared equals 1 minus x squared. And if I move the x squared over, I get x squared plus y squared is equal to 1. And can you recognize what kind of curve this is the equation of? It's a circle. The center would be at the origin, so right here, and the radius of the circle is the square root of this number. Square root of 1 would be 1, so it would have center at 0, 0, and a radius of 1. So it's really a unit circle. Now, if we go back and kind of go back through these 3 equations and go back to this point, notice that normally if I were to take the square root of both sides right here, I would put a plus or minus on the right side. And here I notice there's only a positive square root. I don't have a plus or minus the square root of 1 minus x squared. So y equal the positive square root of 1 minus x squared is not actually the entire unit circle. It's only the upper half. It's only the points that have a positive y coordinate. We don't want any of the points below the x-axis because those would have negative y coordinates. So we actually only get the top half of a unit circle. Center is the origin, the radius is 1, but y is going to be something that's the positive square root of 1 minus x squared. So y will be something that's positive or 0 at the very smallest. So it's all these points whose y coordinates are above the x-axis. So that's what this curve looks like. Let's draw in our rectangle. Our rectangle is supposed to have 2 corners on the x-axis. That's where the 2 lower corners are, and 2 upper corners that are on this circle, on this curve, which is y equals root 1 minus x squared. And then the problem says, for all such rectangles, what are the dimensions of the one with the largest area? So this rectangle could have different dimensions. It could be really wide and skinny in this direction, or it could be very tall and narrow in this direction. And we want to know, out of all those possible rectangles, which one will have the largest area. So we want this area to be as large as possible. And just again to kind of draw for you what the extremes would be, you could have, here's my unit circle, you could have a really long skinny rectangle that has 2 lower corners on the x-axis, 2 upper corners on this circle, or you could have one that's really tall and skinny where you have two upper corners on the circle and two lower corners here. And we want to think out of all those different possible configurations, what would end up giving me the biggest possible area for the green rectangle. Well, what I'd like us to do is to actually label this point over here. I'm going to call x comma y the upper right corner of my rectangle. So notice in particular that it's going to be a point in the first quadrant. So x is going to be greater than or equal to 0 and y is always greater than or equal to 0. So I'll just put that in parentheses. But if I picked this point right here for my x comma y, my x would be negative. So I'm just going to label this point x comma y. It's a point on the unit circle, and it's the particular point where this upper corner hits the unit circle in the first quadrant. If I do that, then we could label this distance here. Well, to get to this point, I go over x, so this distance right here would be x. And to get to this point, I go up y units, so this length is equal to y. Are those actually the dimensions of my rectangle? Well, they're not really the dimensions of my rectangle. My rectangle would be twice as long, would actually be 2x by y. Okay. But we have done this. We've drawn the picture and we've labeled the quantities that vary. X and y could vary. And now what I want us to do is go to the important step 2. Remember, this is a step with a star in it because it's the main function that we're going to concentrate on throughout the whole problem. What function am I asked to maximize? Or sometimes you're asked to minimize a function. But in this case you are asked to maximize something. So what I would like you to do is think about what it is you're asked to maximize and then write that function down as a function of x and y. So pause the video for a moment and see if you can extract that information from the words of the problem. Okay, let's go ahead and try this together. I want to maximize what? It says for all such rectangles, what are the dimensions of the one with the largest area? So I am trying to maximize the area, similar to the problem with the field and the stream. So the thing I want to maximize is the area. And let's see if we can write the area as a function of x and y. Remember, the area isn't just x times y because the dimension of this lower side of our rectangle would actually be x and another x. So this dimension from here to here is actually 2x. So the area would be 2x times y. The width is 2x and the height of that rectangle is y. So that is the function I want to maximize. Well, what's the problem with this? Just like the last example, this is a function of two variables. And we don't know how to find the maximum of a function of two variables. We don't even know how to find the derivative of a function of two variables. You'll learn about that in third semester calculus, multivariable calculus, but we only know how to deal with functions of one variable and how to find the derivative of a function of one variable in this course. So unfortunately, we need to rewrite it as a function of one variable. So we must rewrite a as a function of one variable. Well, how are we going to do that? I'll put a little question mark there. Rewrite, I'll say how. Put a question mark there. So how are we going to do that? How are we going to rewrite a as a function of one variable? And that's where the constraint equation comes in. Now, the constraint equation in this case is both obvious and not obvious. So I want you to pause the video for a moment and see if you can figure out what the constraint equation is. It's an equation that relates y and x together, and it represents the constraint on this problem. Ask yourself, why can't this rectangle just be as huge as it wants? Why can't I have an infinitely large x and an infinitely large y? what is it about the words of the problem that are constraining the size of this rectangle? And then when you've thought about it, or you get stumped, just start the video again. Okay, let's go ahead and think about this together. The reason this green rectangle can't be as big as it wants is that the upper corners have to be inside of this upper half of the unit circle. I can't have them go beyond that, so there's that constraining unit circle, this purple curve, that is our constraint. Well, what's the equation of this purple curve? This is its equation right here. Y equals square root of 1 minus x squared. For us to say that the point x, y lies on the purple curve is the same as saying that this point x comma y satisfies the equation of that curve. That's what it means for a point to be on the purple curve, on the graph of the equation. It means it satisfies the equation. In other words, whatever x and y are, the y coordinate has to equal square root of 1 minus the x squared coordinate, or the x coordinate squared. So the constraint equation actually is the equation of this purple upper half unit circle. So the constraint equation is y equals root 1 minus x squared. That's why I said it's both not obvious, because it's a weird way to find the constraint equation. You have to think about the fact that a point being on the graph of an equation means it satisfies the equation. And yet it's also obvious, because here's the constraint equation. This is an equation that relates x and y together. So it's a perfectly good constraint equation. Okay, let's go ahead and see if we can do step 4. We want to rewrite this function that we were asked to maximize as a function of one variable instead of a function of two variables. So we have to think about how to do that. And so go ahead and pause the video, try to do step 4, try to rewrite the function to be maximized as a function of one variable, and then go ahead and restart the video and we'll do it together. Okay, so the function we want to maximize is our main function that we have the red star by. It's the function from step 2, and we know that's 2xy. If we look at our constraint equation, y is already isolated on one side, so we have what y is in terms of x, and we don't have to do any solving there. So what we are saying is that y is the same thing as root 1 minus x squared. So I might as well take this y down here in the function I want to maximize and substitute root 1 minus x squared in place of y. So what will I get? I'll get a equals 2x times root 1 minus x squared, and now I have the area written as a function of just one variable. That's something that we can handle. And since it's a function of just x, we often at this point write a of x. So that's the area purely in terms of x. Okay, let's go ahead and think about the range of possible x values. That can be a little bit tricky. I want you to pause the video and think about it yourself, and as you think about it, look at the picture here. Remember, x is the x coordinate of this point on the top half of the unit circle, and we said specifically it's a point in the first quadrant rather than the point over here that's in the second quadrant. And you might notice that we already mentioned that if it's the x coordinate of the point in the first quadrant, x has to be greater than or equal to 0. So see if you can decide what the constraints on x are. We said it has to be greater than or equal to 0, but what about the right-hand constraint? Probably the easiest way to answer this question in this case is simply to think about the picture. Think about, well, this rectangle has to have 2 points on the purple half circle, but what could that rectangle look like? It could actually look like a very long, skinny rectangle. So here's my half circle. So it could look like this. Something that's very long and skinny, where this point is closer and closer to the x-axis here. So I could have a long skinny rectangle, such as this, and if I thought of this point getting all the way down to the x-axis and making my y-coordinate as small as possible, what's the very largest this x-coordinate could extend out to? Well, it can't extend beyond the circle, and remember the circle hits the x-axis at a value of 1. So the biggest value x could possibly be would be when this rectangle degenerates into just a line segment, and that would be when this green point comes right down and is right on top of this purple point where the circle meets the x-axis. And so the very largest value x could have is 1. Another way to get the same answer here is to simply look at the constraint equation. So remember, when looking for this range of values, you can either look at the picture, we did the same thing in the last example, or you can look at the constraint equation. And if you consider the constraint equation, you notice the constraint equation says y is equal to square root of 1 minus x squared. Well, this is a function of x, but it's only defined for certain values of x. Remember, we can't take the square root of a negative, so 1 minus x squared, what's under the square root, has to be greater than or equal to 0. And if you were to solve that quadratic inequality by factoring, finding the zeros, setting up a number line, you would find that it would be all x's between -1 and +1 would make 1 minus x squared greater than or equal to 0. So x would have to be in this range of values. But because of the fact that x is the x-coordinate of a point just in the first quadrant, we know that x also has to be greater than or equal to 0. And so we'd really get not x between -1 and 1. We'd actually get x between 0 and 1, because we specifically said we wanted the xy point here to be the point on the circle, but in the first quadrant. But sometimes it's just easier to just look at the picture and think about the extreme rectangles that you could get, either a long skinny one along the x-axis or a long skinny one along the y-axis. And that will give you your largest and smallest x values as well. You can see here for a long skinny one along the y-axis, the very smallest x-coordinate you could have would be an x-coordinate of 0. So this point can range from here, where the x-coordinate is 0, down to here, where the x-coordinate would be 1. I think that's the easiest way in this particular example. Okay, let's go ahead and look at the next page and see what it says. I'm going to set this right next to us, but I'll put it back on top if I need to talk extensively about it. Remember step 5, we're supposed to find the absolute maximum. It should really be, say here, of the function we're asked to maximize, in other words, of a of x. So remember, our a of x is this function. A of x is 2x, and instead of writing square root, I'm going to write 1 minus x squared to the 1/2, and write that square root of 1 minus x squared with a fractional exponent. And we're trying to find the absolute maximum output of this function, the biggest possible area for x's in this range, for x in the interval from 0 to 1. You might want to ask yourself, is this a continuous function, at least on this closed interval? I can see it's a closed interval. And you can check yourself that the only place that the square root of 1 minus x squared would be discontinuous would be outside of the interval from -1 to 1. So this function 2x, which is a polynomial, times root 1 minus x squared, which is continuous everywhere on the interval from -1 to 1, that combination, that product, will be something that's continuous everywhere on this closed interval. So the a of x we've got is a continuous function on a closed interval. That means we can use that easier two-step method to determine what the absolute maximum of our function a of x is. So let's remember what those two steps are. First step, we find all the critical numbers. Find critical numbers. And what do we have to do to find the critical numbers? Well, we have to find the derivative. And unfortunately, in this case, the derivative looks a little bit trickier, but you've had a lot of practice finding derivatives at this point. Let's look at a of x and decide what rule I need to find a prime of x. Well, to find a prime of x, unfortunately, is a product of two functions. It's 2x times this 1 minus x squared to the 1/2 power. So it is a product of two things, and I will have to use the product rule to find the derivative. Well, let's just put the pattern for the product rule up here, where I'm thinking of 2x as my f and this other whole thing as my g, and thinking of it as an f times g. Product rule says we do the first function times derivative of the second plus the second function times derivative of the first. So f times g prime plus g times f prime. Okay, so I use the original first function, that's 2x. Then I'm supposed to multiply by the derivative of the second. That's 1 minus x squared raised to the 1/2. And that looks like a pretty difficult derivative to do. So I'm going to skip that for now and just make use of my operator notation, and I'm going to say times the derivative of 1 minus x squared to the 1/2, and that way I don't have to do it until the next step. So this is my first function times derivative of my second, but I'm leaving that for the next step so I don't try to apply two rules all in one step. Plus, now I'm supposed to do the second function, that's easy, 1 minus x squared to the 1/2 times derivative of the first, and that's so easy I'm just going to do it. So derivative of 2x is just 2. Alright, well, we do still have one derivative left to do. We have to do this derivative. So we have to think about what rule do I need to do that derivative. I'm going to write down the 2x and just carry that factor down. Now we're concentrating on this. It's got an inner function and an outer function. It's a composition of two functions. So I'm going to call this inner function now my g, and the outer function I'll think of as the f. It's a composition of two functions, so what rule do I need to find the derivative? I need the chain rule. And that's why it's probably good that we waited until the next step as soon as we saw this looked kind of complicated, because then we're not trying to do everything all in one line, where a lot of times people will miss an entire factor somewhere or an entire term because you get so wound up doing this derivative you might have forgotten about the g times f prime and the product rule, something like that. Okay, chain rule. So we've done a lot of chain rules now, so that's not so hard. I do derivative of the outer, so it's 1/2, and then it's going to be whatever I plug in to one lower power. So I want to take 1/2 and subtract 1 from that exponent. 1/2 minus 1 would be negative 1/2. Remember, we evaluate that at the original inner function, so 1 minus x squared goes inside. But by the chain rule, I have to remember to multiply by derivative of this inner function. Derivative of 1 minus x squared would be a negative 2x. So this is the derivative that we had left to do. Derivative of the outer, evaluated at the inner, times derivative of the inner. And now I still have this other term to pull down, so let me pull that down. I'm going to put the 2 in front. 2 times 1 minus x squared to the 1/2. Okay, let me clean things up a little bit. One thing I notice is that this is a negative exponent, so I'm going to push the 1 minus x squared to the negative 1/2. I'm going to push that into the denominator to change it to a positive exponent. And what else do I notice? I notice these 2's will cancel out, so I might as well get rid of those. So this term can actually clean up quite a lot. I have an x times a negative 2x. That would become a negative 2x squared in the top. And in the bottom, I would now have 1 minus x squared to the positive 1/2. And this is a plus 2 times 1 minus x squared to the positive 1/2. Let me see if I can write this half a little bit clearer. So that's a 1/2 there. Well, we want to know where the critical numbers are. In other words, places where a prime is 0 or where a prime is undefined. And unfortunately, it's hard to do that when we have two terms like this. It's much easier if it's all written as a single fraction. So let's go ahead and do that. How do I do that? I'm going to write this as over 1, and then I'm going to go ahead and try to get a common denominator so that I can add these fractions together. Well, this has a denominator of 1. I need it to have this denominator, so I'm going to multiply this denominator by 1 minus x squared to the 1/2. But of course I can't just multiply the bottom by that. To balance my fraction, I have to multiply the top by exactly the same amount. And let's see what we end up with. Well, I will get a minus 2x squared all divided by 1 minus x squared to the 1/2 plus, and over here, this 1 minus x squared to the 1/2 times another 1 minus x squared to the 1/2. Remember, when we multiply like bases, we add the exponents. So I have a 2 out in front, and when I add those exponents, it looks like I'll get 1 minus x squared to the first, all divided by this new denominator, this common denominator of 1 minus x squared, all raised to the 1/2. Well, that's great because I can go ahead and combine those into a single fraction. So let's go ahead and do that. In the denominator, I have a 1 minus x squared to the 1/2. I'm going to write that as square root of 1 minus x squared, just so that it's a little easier for me to understand exactly what that fractional exponent means. In the numerator, if you look at it, you have a negative 2x squared from this numerator. You're going to add to that what we get when we multiply these out. When I multiply those out, it looks like I'm going to get a 2 minus 2x squared. So I add that to this numerator, and it looks like I will get 2 minus 4x squared. I add this negative 2x squared and that negative 2x squared. Well, let's factor everything as far as we can. It looks like I could pull a 2 out of the top. Let me do that. So I have 2 times 1 minus 2x squared in the top. In the bottom, if you want to, you can go ahead and factor this, or we can just think about what values of x make that 0. Either way is okay. But it would factor into a 1 plus x and a 1 minus x if we were to factor what's underneath the square root. Well, I know I'm running into my space for part 6, but let's go ahead then and figure out what the critical numbers for A are. And remember, we're looking for places where either this expression, which is our derivative, this is our expression for A prime of x, we're looking for places where this is either 0 or undefined. Well, this expression will be 0 when the top is 0, and the top will be 0 when 1 minus 2x squared is equal to 0. And when is that true? I'll move the 2x squared over to the right. I get 1/2 equals x squared. So it looks like when x is either 1 over root 2 or negative 1 over root 2. Those would be the two critical numbers that I get from setting the numerator equal to 0. And then there are also critical numbers where the derivative, let me put a good prime mark there, where the derivative is undefined. That would be anywhere where the denominator is 0. So these are the values that make my first derivative equal to 0. But we can also get critical numbers by looking for where a prime of x is undefined, and it's undefined when its denominator is 0. And I can see that'll be when x equals negative 1 or x equals positive 1. Now, don't forget that we are really just looking for the absolute maximum on a particular interval. And the particular interval I'm interested in is the interval from 0 to 1. So I only want to know what's the biggest output value of this function for x's in that interval, and I don't care what happens if x is bigger than 1 or less than negative 1. So when I look down at these critical numbers, I only have to consider the ones that are in the interval from 0 to 1. 1 over root 2, that's 1 over about 1.4. That's something that's between 0 and 1. You could put it into a calculator. I think it's about 0.7. So that falls in this interval. So that's one of the ones I want to consider. But what about negative 1 over root 2? That is definitely not in the interval of x values between 0 and 2, so I don't even have to consider that one because I don't care about the absolute maximum, a bigger maximum that would happen outside of my interval. Negative 1, do I want to consider that one? No, it is not in my interval, so I don't care about it. X equal 1, would that be in my interval? Well, since it's a closed interval, it does contain this endpoint of 1, and so I do have to consider that one. Remember now in step, I'm going to sort of cross this out because we're really still doing part 5 here because I just ran out of room. Remember in step 2 of our two-step method for finding the absolute maximum of a continuous function on a closed interval, all we do is we now figure out what the value of the original function a is at each of the critical numbers, and then we find out its value at each of the endpoint numbers. So we have to check the value of a at the critical numbers that fall within our interval and at the endpoint numbers. Well, we only had 2 critical numbers that were within our interval from 0 to 1. One of them was 1 over root 2, and the other one was 1. And our endpoint values, well, 1 happens to also be an endpoint value, so that one will have already checked, but 0 was an endpoint value that I hadn't included up here, and so I need to check the value of a at 0. Okay, so I'm plugging these back into the original function, and I'm going to use my notes to cheat a little bit here so that I can actually find what those values are. Well, why don't we actually plug it in? I'm plugging in 1 over root 2 into this function. So I'm really doing 2 times, I'm replacing x with 1 over root 2, and then it's times, instead of a fractional exponent, I'm going to use the square root, 1 minus my 1 over root 2 squared, and that would be a evaluated at 1 over root 2. Well, this looks terribly complicated, but it's actually not too bad. Remember, 2 can be written as root 2 times root 2. So one of those root 2's actually cancels with the root 2 down here, and 2 over root 2 simplifies to just square root of 2. If you're not sure about that, just multiply top and bottom by root 2 and cancel, reduce, and you'll see that you end up with a root 2 there. For this one, it's going to be square root of 1 minus, well, 1 over root 2 squared is just 1/2. So it looks to me as if I end up with square root of 2 times square root of 1/2, which would be 1 over root 2. It looks to me as if I end up with the number 1. And so that's the area of my rectangle, the green rectangle that I had originally, when x equals 1 over root 2. Now we can try to find the value of this function at 1 and at 0. That's quite a lot easier. When I plug 1 in here, I get 2 times 1 times the square root of 1 minus 1 squared. Well, 1 minus 1 squared is 0, so this whole thing becomes, I'm just going to put it here at the very end, 0. So when x equals 1, you get an area of 0 for your rectangle. That should make sense. That's sort of when we had this really long skinny rectangle. Oh, actually it's this really long skinny rectangle, and x was equal to 0. When one of the dimensions of your rectangle is 0, your whole area is going to be 0. And you can check yourself when you plug in 0. That's pretty easy to see. You'll have 2 times 0 times root 1 minus 0 squared. So again, you get 0 for an output. So if we choose either the endpoint values, we get an area of 0. When we choose a equal to this critical number, 1 over root 2, we got an area of 1. We are looking for the absolute maximum area, so it wouldn't be these values. They would actually be the absolute minimum area for x's in this interval. This would be the maximum possible area. The most we can get is an area of 1. If we're working in meters, say, it would be 1 square meter. So that's my absolute maximum, and notice it occurs when x equals 1 over root 2. Now the only thing we have left to do is to figure out what the corresponding y value is. We were supposed to find the dimensions of our rectangle. We know what the x value is. The x value is 1 over root 2. Now we just find the y value, and that's really part 6. So I'm going to put step 6 down here. We want to find the corresponding y value. And how do we do that? Remember, it's easiest to go back to the constraint equation. So if you remember, our constraint equation was this one that we found in step 3, y equals root 1 minus x squared. And maybe because I've run out of space on the other overhead, I'll just go ahead and plug in. I want to know what's y when x is equal to 1 over root 2. I just want the corresponding y value. So I'm figuring out square root of 1 minus 1 over root 2 squared. We actually did this calculation for part of figuring out the area just a moment ago, but it's 1 minus 1 over root 2 times 1 over root 2 is 1 over 2, and so I end up getting square root of 1/2, and square root of 1 is 1 over square root of 2. So the y value turns out to be square root 1 over square root of 2, as well as the x value that maximizes that area. Well, let's write down a final answer on our other sheet. So we found that the x value that gives us a maximum area is 1 over root 2, and the corresponding y value was also 1 over root 2 when we plug back into the constraint equation. However, I should just mention that those are not actually the dimensions of our rectangle. So let's go ahead and think about what the dimensions of our rectangle are. Remember that the rectangle was not x by y. If we look back at this picture, the rectangle was 2x by y, and so our dimensions should be 2 times our x value by our y value. So I have to double the x to get the actual width of the whole green rectangle. So the dimensions would be 2 times this x value. So that would be 2 times 1 over root 2. And 2 times 1 over root 2, we actually did that simplification already. 2 is root 2 times root 2. It cancels with the root 2 in the denominator, and you get root 2. So the dimensions would actually be 2x, which is root 2, by 1 over root 2. You can rationalize that denominator if you want to and write it as root 2 over 2, but either way is okay. So we would say the dimensions of our rectangle are 2x by y. 2x turns out to be square root of 2, and y turns out to be 1 over square root of 2. Okay, let's go ahead and look at our next example.